Hello guys. In the previous video, we discussed about bipolar junction transistor, and we just introduced the concept of bipolar junction transistor, the forward active mode, and we discussed why the base width should be small, right? And we discussed that the from the emitter in a NPN bipolar junction transistor from the emitter, the electron concentration will be diffused through the base region and will reach to the collector end, so that way it will produce the current. So today we are going to discuss about the collector, emitter, and base currents in a bipolar junction transistor. So let us start that. So today's topic is collector, emitter, and base currents in uh, bipolar junction transistor. Okay, so this is today's topic that we are going to discuss in detail. So let us start with that. So in PN junction chapter, we have already derived the minority carrier concentration and we determined the current, right? The same principle we will use here. So before deriving the concept, let us just see how the minority concentration in all the emitter, base, and collector region look like. Okay, so here if I will draw the concentration, suppose this is our emitter region, which is N in an NPN transistor. So this is the space charge width, the boundary between emitter and the base. Base is made up of P. Okay, and then we have the space charge region between base and the collector. Then we have the collector, which is made up of N type material. Okay, so now here if I will show you this in the forward active mode, we know that the base emitter junction is forward biased, right? And the base collector junction is reverse biased. So that is what we call forward active mode, right? So now if I will show you the concentration, minority carrier concentrations, okay, in different regions, right? So here if you will see the pole will be considered as the minority carrier concentration, and we have already done this in our PN junction chapter. You can revisit the video, the minority carrier concentration distribution in PN junction. So here we got, this is our variation of the hole in the N region. So I'm writing it as Pn and a function of X, of course. And this is the thermal equilibrium concentration, which is Pn0, right? Then in the base region, similarly, we have the emitter from the emitter, the the depends upon base emitter voltage, right? And it is maximum here at the edge of the space charge width, and then it will go here. It should come to the equilibrium position. Suppose the equilibrium position is somewhere here. Okay, I mean the minority electron concentration in the P region or the base region, it should ideally be, we can write this as suppose NB0, okay, that is in the base region. Then ideally it should come to that value NB0, but our base collector region is reverse biased. So in reverse bias, the minority carrier concentration at the edge of the space charge region should be 0. So it will fall back to 0 like this. So this is the minority electron concentration in the P region or the base region, and the function is given by this. This value, if you remember, we have already derived in PN junction, and I can write it as NB, that is concentration of electron in the base region at X is equal to 0. So we have taken this width of the base region, this is X is equal to 0, and this is X is equal to XB. So XB, we have considered the width of the base region. So this NB0 we have derived, if you can go back and check, if you have forgotten the derivation, and exponential e to the power VBE base emitter voltage, or it was there written as VA forward bias applied voltage, and then VT here thermal voltage, where you have um, NB0 is equal to NB at x equals to 0 is NB0 e to the power VBE divided by VT. Okay. So this is what we have already derived, right? Now, the first thing that we are going to derive here is the collector current. So how we will find the collector current? Okay, so let us see what is collector current and how we can derive the collector current in BJT in forward active mode. Okay, so let us write the collector current first. Collector current. So now the collector current, we can write it as a diffusion current. Okay, diffusion current. In what diffusion, why we will write it as diffusion current? You can see the electrons, okay, majority carrier electron concentration in the emitter is high enough. So electrons from the emitter side, they will diffuse to the base and then will diffuse to the collector region. Okay, so electron flow, so I will show you the direction of current as this. Okay, so this is the collector current, and mathematically we will treat this collector current and we will derive. So we can write the collector current as diffusion current. So we have already derived the diffusion current. You can go back to the video of diffusion current and how it is derived. So I can write this as E, okay, and this is the diffusion coefficient for electron, okay, and this is the area through which the electron moves, that is the BE. ABE I'm writing, okay, as it is moving from E to C, reaching to C through B, so I'm writing that area, okay, and we have the dnx, one dx. So this is derived from the diffusion current expression, current density, which was Jn is equal to E dn by dx. Okay, this is what we have already derived. So current density we have, so current density is actually In divided by A, area. So for I have multiplied this factor, area factor here. Okay, so this is simple. You can just revisit the concept of the diffusion current. Okay, so now from that we can just continue. We can write this IC collector current is EDN. Okay, we have the area ABE, and then we will write this as a dN by dx, which is the variation of electron concentration. You can see in the base region, which is NB at x is equal to 0 here, and you can see here it is 0, and here you sorry, NB at x equal to 0, the value is given as NB0 EVV by VT, and here it is 0. So we can write this as the concentration at x is equal to 0 is NB0 minus the concentration at x is equal to XB is 0 divided by the width dN by dx, we said. So 0 minus XB, that's the width of the base region. So we got this. Now this can be written as, after substituting the value, okay, so we got this minus XB. So E D N A B E, and then NB at x is equal to 0 divided by XB. Okay, and you substitute your NB0 value. NB at x is equal to 0 was, we have already written this NB0 and then exponential e to the power VBE divided by VT. Okay, VT. And you, if you remember this VB, this value VT is actually your KT by E in the derivation we have used. This is our thermal voltage, we said. Okay, so now if I'll substitute this, finally we got as minus E dn ABE divided by XB NB0 and then exponential of e to the power VBE divided by VT. Okay, so this is the expression for the collector current that we obtained. Okay, now one thing we can write from here, in terms of saturation current, okay, so that we can write IC is equal to IS, okay, and this exponential term as VBE divided by VBE divided by VT, okay, VBE divided by VT. Okay, so this can be written where IS is equal to whatever minus EDNAB by XB NB0, right? So I see the collector current is directly proportional to exponential of VBE divided by VT. Okay, so this is what we got. So it depends upon the base emitter voltage, right? The collector current depends on this. Okay, so of course we got this IC is controlled by the base emitter voltage. Okay, now let us move to the emitter current. So we are done with the collector part. Now let us move to the emitter current. Okay, and how we can derive the emitter current now. Okay, now emitter current, if you will see, it has two parts. Okay, one is due to the flow of electrons, right, injected from emitter to the base, right? Okay, so that part we will write it as IE1, the first component of emitter current. Okay, that is because of the electrons moving from emitter to the base, right? Yeah, and the second one will be due to the majority carrier holes in the base. Okay, so holes in the base are injected across the base emitter junction. Okay, base emitter junction into the emitter. These injected holes produce a PN junction current as well. So that we will take as IE2. Okay. So this component of emitter current is not part of the collector current because this IE1 that actually reaches to your collector, right, which we have already determined, like what is the collector current. But this IE2 that we got because of the injection of holes from the base towards the emitter that we have not considered, right? So this is because of the electrons getting injected from emitter to base, but holes we have not considered. So that part of the emitter current component will be there. Okay, so if I'll just rewrite this, we can write IE2, the component, okay, due to the injection of holes from the base to the emitter, right? That we can write. Suppose I will write just IS2, okay, from the diffusion current expression, exponential of VBE by VT, right? Definitely it will also depend upon the base emitter voltage, okay? And IE1, we have already discussed that it is the collector current, which we have written as IS exponential of VBE by VT, right? Here, just to distinguish it from IE1, you can see the reverse saturation current we have taken different, but the whole depends upon the whole concentration, how many holes are actually getting injected from the base to the emitter region, that will decide the IS2 factor. However, definitely it depends upon the base emitter voltage. Yeah. So here one thing you can see that our IE, the total emitter current, which is because of both the components IE1 and IE2, and both of them depends upon this exponential e to the power VB by VT, and here also e to the power VB by VT. So we can write I see we have already obtained that it is directly proportional to the VBE by VT, and IE also. Now we got both the components, they depend on the base emitter voltage, so exponential of VBE by VT. But here you got IE is greater than IC because you got both the components and one component of emitter current is equal to the collector current. So that's the reason we got IE is greater than IC. So if you take the ratio between these two current components IC and IE, that will be a constant which we write as alpha, and we call it common base current gain. So we call it common base current gain. Now just I just said I see the collector current is less than IE, so the ratio between them, that is alpha, will always be less than 1. Okay. Okay, so this is what we got. But IE2 is not part of the basic transistor action, okay, and considered as very small. Okay, so this IE2 is the amount of hole that is getting injected from the base region to the emitter region and is considered to be very, very small. Okay, that depends upon the doping profile as well. Okay, so the common base current gain will be close to 1. Okay, so this is what. Okay, now collector current is independent of the base collector voltage. If you now go back, okay, the collector current here is independent of the base collector voltage, okay, as long as the base collector junction is reverse biased. Okay, so base collector junction is reverse biased, so the collector current is independent of the base collector voltage. Okay, now if you will see the basic circuit will look like this is, suppose I will name it as VBB, and then it goes here, and we have a register defined here RB, right, and is connected this way. So this is our bipolar junction transistor, okay, and this is our N region, okay, that is the emitter region, and this is the base region, which is P region. Of course, the base is the P region, right? And then again, N you got, which is your collector. Okay, so I will just name this as E emitter, and this one is base, and this one is your collector, right? Okay, now here, okay, we will keep the emitter. Now you can check. So one is the base emitter connection. Here you can see this is the base emitter, right, and then the collector is also connected to the emitter in this case, right? So in the previous case we just saw that the base was common. Now here we kept the emitter as common. Okay, in between I can just put register this, okay, and then the voltage across the collector and emitter. Okay, so let us connect this. Okay, let us write this as VCC, and the resistance here is ours. Okay, so this is what we got. Now, if I will ask you what is VCC here, VCC can be written as I see the collector current multiplied with the resistance. Okay, then we have the VCB here, we have VCB, the potential here across C and B, and then we have the potential here across this base and emitter, which is VBE, right? So VCC here can be written as ICRC plus VCB plus VDE. Okay, that can be written for this loop. Okay, so here if you will plot a graph between PCE versus IC, common here collector emitter voltage, okay, collector emitter voltage, and this collector current. Then here for forward active mode, collector emitter, okay, so you will see graphs like this. Okay, so it will keep on increasing, will go, and then will be like this. Okay, and further you increase, and then you see this. Okay, so here you can see, okay, this is the saturation result. Okay, so VCE and collector current. Okay, similarly, if you will plot VCB and IC, then what will happen? This is collector emitter voltage and collector current we got, right? And now if I will increase the collector base voltage and will measure the value of collector current, then you will see, so this is, if you will see, this is alpha times IE1. IE1 was the component of emitter current, that is because of the injection of electrons from the emitter region through the base and reach to the collector. So this is if your IE1. Okay, so now you can see IC collector current depends upon the component IE1. Then you multiply it with alpha, okay, which was your common base current gain, and then you will get the IC value. Okay, similarly, another value, if I will just take this as IE2, then I will get this as alpha times IE2 this way. Okay, similarly, another value of IE3, then you got alpha times IE3. So this will be okay. So doesn't depend upon the value of voltage. You can see, so VCB, you keep on increasing VCB, IC remains the same, right? Because it depends upon the emitter current. Okay? So these are all ideal bipolar transistor common base current voltage characteristics. Let me ask you. Okay, now let us move to the base current. Okay, base current. Now in the base current, the component of emitter current IE2 that we discussed, right? So IE2 was the whole concentration moving from the base to the emitter region, right? If you remember this was your IE2 we considered, right? So the component of emitter current IE2 is a base emitter junction current, right? So this current is also a component of base current IB1. So we will consider that IE2 as one of the components for the base current. So IE2 is your IB1, right? That is involved. This component of current is proportional to e to the power VV by VT that we have already considered. So this one was proportional to exponential to the power E because it depends upon the base emitter voltage V divided by VT, right? So there will be some recombination of minority concentration, minority electrons with majority holes in the base, because when electrons are moving from the emitter towards the base, there will be some amount of recombination. Electrons will be recombined with holes, right? So that possibility is there. So since majority carrier holes in the base are disappearing, they must be resupplied by a flow of positive charge, okay, into the base terminal, right? So in the base region, we have concentration of holes more. Now the electrons, those are moving from the emitter to the base. Here they will vanish or disappear these holes, right? So whatever amount of holes are now disappearing because of the injection of electrons from the emitter region to the base region, we should supply that amount of extra positive charge, right? So that the, the equilibrium concentration should be maintained here. So that flow of positive charge, if we will consider this flow of charge, we can consider another component of current, which is IB2. Now the number of holes per unit time recombining, okay, in the base is directly related to the minority carrier electrons in the base, which is proportional to e to the power VV by VT. So what we said, now number of electrons are moving from here to this, right? Okay, and that what number of electrons are, moving from the emitter to the base, that depends upon, that is directly proportional to VBE by VT, right? So this same factor will be responsible for what vanish of these holes in the base region, and we are resupplying the same current over here, so that this component is also directly proportional to, IB2 is directly proportional to exponential of VBE by VT. So using this logical approach, we can write that the base current, okay, is directly proportional to the power VBE by VT. So one component of the base current was exactly the same as one component of emitter current, which was proportional to exponential to the power VA to the power VB by VT, right? The second component is because of the recombination of holes with the electrons that we consider. So number of electrons moving from emitter to the base depends upon exponential VB by VT. So the amount that is needed, right, the extra supply of the charge, positive charge, that also will be equivalent to or directly proportional to e to the power VB by VT, right? So IB, the base current, will also be together directly proportional to exponential to the power VB by VT. Okay. So now what we will do, if we will take the ratio between these two, IC and IB, that will be a constant because both IC and IB are directly proportional to exponential of VB by VT, right? So IC is much larger than this IB, right? So this beta that we have written is known as common emitter current gain. Okay, common emitter current gain, right? So beta is here for silicon bipolar junction transistors. For silicon, most of the silicon BJTs, okay, depending upon the internal transistor structure, like the width and dimensions and all, and also the doping concentrations, right? Okay, which are, this value beta for silicon BJTs, right? This beta is approximately 100, of the order of 100, right? So 100 times than the base current. Okay, collector current is 100 times the base current, but it depends upon the structure of the transistor and also the doping profile of each region, right? And normally these are optimized for high gain and application purpose in the electric circuits. Okay, hope you understood this lecture. Thank you. We will continue in the next video. Thanks for watching.